SwayamPrabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In module 15, we will be continuing what we have been seeing earlier also, that organic transformations and reagents, functional group interconversions, oxidations and reductions. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, Ministry of Education, New Delhi. What we will be looking at in this session include, we will be looking at various redox reactions and reagents, mainly diol H reduction or lithium and liquid ammonia reduction, use of Lindlar catalyst or pelletized carbon, and we will also be looking at other oxidation reactions, sharp plus oxidation, use of potassium ferricyanide. So these are all some of the reagents that will be used. And we will also looking at main wall rearrangement, sharp plus oxidation, Betz reduction, Luce reduction, and various other reactions. There are few references I had given here. Those who are interested to know more can actually visit these websites, and you can also download these files and you can read more about these kind of reactions. Let us look at the first problem. So the major product formed in the following reaction sequences are: first, we have a alkene that is given here, and this is treated with metachloroperoxybenzoic acid, followed by reaction with the BF3 etherate. This is nothing but the Lewis acid. So the MCPBA reaction will generally give a epoxide, and once the epoxide is formed, we are going to see how the Lewis acid is going to interact with the epoxide and what is the product that is going to be formed. So if you look at the final product that is formed, the first one is the aromatized system. This is quite unlikely when we do the simple epoxidation followed by Lewis acid reaction. So this can be ruled out. So we have A, B, C and D are the probable products that can be formed in this reaction. So in the B case, what happens is we still have the alkene unit. So that is again quite not going to happen, because when you epoxidize, the double bond is actually going to disappear. So B is also ruled out, A is ruled out. Then we only have C and D. In the C and D, the only difference is we end up with a carbonyl compound, but only the position of the carbonyl group is a little bit different. So we are going to find out which is going to be the right product based on the reaction mechanism. So if you look at the reaction is, as we have seen earlier, the MCPBA generally epoxidizes the alkenic double bond. So we end up with the alkene, this epoxide as shown here. So we already know there is a electrophilic oxygen that is getting transferred to the alkene bond, so that we end up with the cis epoxide. So in all the cases, we have only the cis epoxide that is formed when we treat an alkene with the metachloroperoxybenzoic acid. So what is the next step? Then epoxide is now treated with the Lewis acid, BF3 etherate. Oxygen has lone pair of electron, that is electron rich. Boron trifluoride is basically a electron deficient element, so that requires electrons. So what happens is the lone pair of electron is shifted between oxygen and boron, and we end up with a bond that is formed between oxygen and boron. So this is what is the oxonium ion formation, is the one that happens when the Lewis acid reacts with the epoxide. So once this happens, what is the next step is the most crucial one. The epoxide now opens up. So the epoxide opens up via the hydride ion shift. So this is the most crucial one. So here this carbon is the one that actually shifts the hydrogen atom from that hydride 1,2 hydride shift takes place, and this 1,2 hydride shift leading to the formation of the bond on the next adjacent carbon. This is not the position number 1, only the second position is the place where the oxide is actually opening up. So we end up with the carbonyl unit on this second carbon. So this type of rearrangement, that is during this opening up of the BF3 group, is also lost, and because this Lewis acid is lost concomitantly, and we end up with the corresponding carbonyl compound, and this type of rearrangement is called main walled rearrangement, and the obtained product is basically the ketone. Let us move on to the next problem. So here the major product formed in the following reaction sequences. There is a lactone that is given here. This lactone is now treated with the diisobutyl aluminum hydride, that is dibal H, that is one equivalent of the reducing agent is used. This is step number 1, and in the step number 2 we are treating that compound with the
vinyl magnesium bromide.
So this is nothing but the Grignard reaction that we are going to carry out, and in the third step we are going to oxidize the product whatever is formed in this particular Grignard reaction to the corresponding oxidized product by pyridinium chlorochromate. So these are all the 3 reaction sequences which are happening, and we have to identify what is going to be the product. So when we carry out a reduction on the lactone in the presence of dibal H, dibal H generally reduces esters. If we use 2 equivalent, we end up with an alcohol. If we use 1 equivalent, we end up with an aldehyde. So this is the normal ester reduction. But when we reduce a cyclic ester, that is lactone, we end up with a lactol as the product, and the lactol can actually undergo Grignard reaction with the Grignard reagent. So that is what is going to happen. So if you look at that thing, we have 4 options that are possible here, and we are going to identify which could be the product, which could not be the product, because when the lactone is undergoing dibal H reduction followed by Grignard reagent, obviously this lactol or here what we have is this product is a furan ring. This is also the reduced furan ring. So these 2 are quite unlikely will be retained. In other words, we can say B and C cannot be existing, because when the Grignard reaction occurs, this actually opens up the lactol ring. So that is how the reaction actually proceeds. So we cannot have the furan product as given here. So B and C are ruled out. We have 2 ring opened product that are given, and we have to, if you look at the structures, there is a carbonyl, 2 carbonyl unit. Here we have a 1 carbonyl unit, and we have 1 alkene in the first product, and we have 1 alkene in the final product. So in other words, we have product A and product D both has 1 carbonyl unit and 1 alkene. So these 2 are common in both the cases, but the only thing extra is only the carbonyl, second carbonyl unit is actually present. So based on that, can we identify what is going to the product? It is going to be very difficult to predict. So let us look at the mechanism to find out what is the actual product that is formed. So we take the lactone, and the lactone is treated with 1 equivalent of dibal H. So basically the lactone reduction using dibal H leads to the, because here the hydride ion is transferred. In other words, the carbonyl unit is reduced to a alcohol unit. So that is what if you use 2 equivalent, but if you are using only 1 equivalent, then simply the alcohol unit. If you have a ester or COOR prime and we use 2 equivalent of dibal H, we end up with the alcohol. And if we are using only 1 equivalent, we will end up with the aldehyde, corresponding aldehydic unit. So that is the difference between use of 1 equivalent or 2 equivalent or dibal. Here we are only using 1 equivalent. So this being a cyclic lactone, the carbonyl group only undergoes reduction only 1 equivalent. So we end up with the corresponding hydroxide derivative, that is what is called lactol. So this is the electrophilic carbon, and we have the hydride anion. So the hydride ion is transferred to the electrophilic carbon. The oxygen bonds forms a bond with the aluminium. So we end up with the aluminium alkoxide complex. So this is a tetrahedral intermediate that is formed in this particular reaction. So this is the first step that is happening, and once the tetrahedral intermediate is formed, this is subjected to acidic workup. So at that time, this particular OAl bond is broken, and we end up with the corresponding alcohol unit. So this is basically what we can say is also like a cyclic aldehyde. We have a aldehyde unit and we have a neighboring oxygen hydroxyl unit that is present. If they are present in where they can actually form a cyclic system. So if we break this bond, so here we have a aldehydic unit and we have a hydroxyl unit here. So 1, 2, 3, 4. So if there are 4 atoms apart, then these aldehyde and the hydroxyl can combine to form a lactol. So as shown here. So in this particular case, we actually started off with the lactone. So simple reduction of that gives the lactol, and the lactol can also undergo ring opening. So when the lactol undergoes ring opening, we end up with the aldehyde unit and the alcohol unit. So what will happen is we will end up with the aldehyde on this carbon and we have the hydroxyl unit in this carbon. If that happens, then the next Grignard will not work. The reason why the next Grignard will not work is Grignard is a basic reagent. We have a acidic alcohol unit. Hydrogen atom is acidic in nature. So if we treat a Grignard reagent with any acidic substances, alcohol solvent or amino derivatives or even water, all will destroy the Grignard reagent. So the Grignard reaction will not proceed. So in other words, we can actually say, even though lactol can be considered as a hydroxyaldehyde, in this particular system, we are not having a separate or a discrete aldehyde unit and the alcohol unit that is present. Both are formed only as a lactol unit. So this lactol can now undergo reaction with the Grignard reagent. So once this undergoes a reaction with the Grignard reagent, we end up with a diol as shown here. So this is how the reaction actually proceeds. And once we have a diol, what is going to be the next reaction? The next reaction is reaction with the PCC, pyridinium chlorochromate. So the mechanism of conversion of an alcohol to the ketone we have seen earlier. So this is how the overall process that is happening. So the alcohol, 2 alcohol units that are present, which are the secondary alcohols in this particular case, undergoes oxidation to the corresponding carbonyl, that is the ketone unit, by reaction with pyridinium chlorochromate. So what we can say is our final product has 2 carbonyl unit and an alkene unit. So the product option A is the correct option for this particular reaction. So that way we can say the overall reaction leads to the corresponding product as shown here. So let us move on to the next problem. So here the major product A and B formed in the following reaction sequence are. So there is a alkyne alcohol is given, alkynic alcohol is given as the starting material. This is also having a double bond, alkenic double bond is also present. So we have a double bond, we have a triple bond, and we have a alcohol unit. So these are all the 3 function group that is present in this molecule. This is subjected to reduction using lithium aluminum hydride and also reaction with sodium ethoxide. So we end up with the intermediate A. This intermediate A undergoes Sharpless epoxidation in the presence of L plus DET, diethyl tartrate salt, leading to the product B. And this question was asked in June 2012. And we are going to find out what are all the different products that will be formed. See, whenever we have a alkynic alcohol, that alkynic alcohol undergoes reduction, especially trans reduction by lithium aluminum hydride. So if we look at all the possibilities, in the possibilities, these are A and B 2 substrates, and we have 1, 2, 3 and 4. 4 different options are given. So these 2, A and B, have the trans double bond. 2 and 4 has a cis double bond. So in other words, the reduction of alkynic alcohol using lithium aluminum hydride only gives a trans isomer. So that means 1 or 3 is the most probable product, but not 2 and 4. So that is ruled out. Now we have to find out between 1 and 3 which one is going to be the product. So if you have the double bonds, The sharpless epoxidation is mainly for the allylic alcohols epoxidation. So if we look at 1 and 3, 1 and 3 in both the cases, 1 has both the alkenic double bond and the allylic alcohol is oxidized, so that is one product, and in 3 only the allylic alcohol is oxidized, the alkene is remaining intact. So in other words, allylic sharpless epoxidation cannot oxidize the isolated double bond, so we can rule out 1. So the most probable product is actually, the correct option for this solution is 3 only. So let us look at the mechanism to confirm whether it is actually the case or not. So this way, in some cases, you can also easily work it out without going through the complete mechanism. What is the product? We can also find it out. So let us look at how the reaction actually takes place. Generally, a triple bond is not reduced by lithium aluminum hydride. So alkynes are generally not reduced by lithium aluminum hydride. The only exception is if the alkyne has a neighboring hydroxyl group, then that undergoes a reduction with the help of lithium aluminum hydride. So why or how it is possible is simply because we have a oxygen which is nucleophilic, or which is electron rich in nature, and the lithium aluminum hydride is actually having the electron deficiency, because once it transfers the hydride ion, that aluminum becomes electron deficient. So that lone pair of electrons on the oxygen can be easily given to the aluminum to form a complex. So that is the driving force for this particular reduction to occur. So in the first step, what happens is the lithium aluminum hydride transfers its one of the hydride anion to the carbon atom. So that is so once that particular hydride ion is transferred to this carbon, because this is the same carbon into which the hydroxy unit is actually attached. So this is where the hydride ion, first hydride is transferred. So this oxygen now forms a cyclic intermediate, that is the aluminum alkoxide complex is formed internally, which is a 5-membered ring system, because generally 5-membered ring systems are quite stable. So that is the reason this hydroxide unit, that the hydroxyl group, is facilitating the transfer of hydride ion. When there is no hydroxyl group, the lithium and aluminum hydride will not react with the alkynic triple bond. So when there is there, then only the transfer takes place. So the first hydride ion is transferred. So in the next step, what happens is this aluminum complex is broken by the acidic workup. So that results in the opening up of the alkoxide unit, which results the second hydride ion is transferred actually here. So in other words, the two hydrogen atoms which are transferred are trans to each other. So that is how we can say this alkynic alcohol is converted to the trans allylic alcohol by lithium aluminum hydride reduction. And once the trans allylic alcohol is formed, this will undergo this sharpless epoxidation in the presence of plus DET. So what is the sharpless epoxidation condition? Sharpless epoxidation condition uses tertiary butyl hydroperoxide in the presence of titanium isopropoxide and plus or minus diethyl tartrate. In this particular case, we are using a plus diethyl tartrate as the salt. So sharpless epoxidation is a very, very special and a stereospecific reaction in which, depending on what is the sign of the tartrate, whether it is a plus isomer or the minus isomer, we can effectively say where the epoxidation actually going to take place. So if it is a plus isomer, it is actually going to attack from the bottom face of that allylic alcohol. So how do we know what is the bottom face and other thing? So this is a rectangle that is drawn here as shown, and keeping this hydroxy unit at one corner, another hydrogen at another corner, the alkyl group at another corner, and the another hydrogen at the other corner. So in other words, we have a trans alcohol here. So that is the simplest thing we can remember easily. So all these groups are pointing towards the corners of the rectangle box, And once this is a planar one, because we have a alkenic bond is a sp2 hybridized carbon atom, so they are planar in nature. So the diethyl tartrate catalyzed epoxidation reaction actually introduces the oxygen from the bottom face of this one. That is how we say. So this is how we can write, like formed product is shown as given here, and this double bond does not undergo any reaction. So let us move on to the next workout problem. The major product A and B formed in the reaction as we have a couple of alkynic bonds are given here. Here also we have the allylic alcohol type hydroxy units are given here. We are going to reduce that with the hydrogen in the presence of Lindlar catalyst. That leads to the product A, and this on heating gives product B. This question was asked in December 2019, and we have various combinations that are given. What are all the different products that will be formed? One thing we have to remember before solving this problem is what is the role of Lindlar catalyst, and how does it reduce, whether it reduces the triple bond or whether it reduces a double bond, or what is the role of this Lindlar catalyst, we need to know. Once we know that, then it becomes very easy for us to solve the problem. Basically, the Lindlar catalyst is a very specific catalyst. This reduces only the alkynes. This does not reduce alkene. So that is point number 1. 2, when it reduces, we have a very specific product formation, that is the cis reduction that is happening. So these are all the 2 things we have to keep in mind. So before we look at the reactions, we have 4 different products that are given, and if you look at the first and A-B combinations, the starting material has 2E and 8E. So this carbon and this allylic units are having E configuration, that is the trans isomer that is present, and this undergoes reduction to give cis isomer, because Lindlar catalyst reduction leads to cis isomer. So that is the main thing we have to keep in mind. Based on that, we can easily figure it out, what are possible, what are not possible. So if you look at option 1 and option 3, we have in one case we have 4E isomer, in another case we have 4Z isomer. So if we look at these 2 things, we have 2 alkenic bonds are there. So when 2 alkenic bonds are there, both of them will reduce to the cis isomer only. So in other words, we have the other one as the trans product. So when we have the out of the 2 double bond, one is reduced as a cis isomer, another one is reduced as the trans isomer, means that cannot happen in the Lindlar case. So these 2 possibilities are completely ruled out. If you look at the other 2, even though the structure is drawn in a different way, if you look at the name of the compound, these are one and the same compound. The first one is 2E, second one is 4Z, third one is 6Z, and fourth one is the 8E. So here again it is 2E, 4Z, 6Z, and 8E. So that means the stereochemistry remains one and the same. And if you look at the name of the compound, that is also same. The only thing is the molecule is written differently, just to confuse you. So don't get confused by that. In that case, these 2 options are possible. Starting materials are the intermediates in that reaction, and these undergo cyclization to give our final product. Now let us look at how the reaction actually proceeds. So in the first reduction reaction, only the alkyne triple bonds are reduced by Lindlar catalyst, and this reduction always leads to the cis product. So it does not reduce the alkene. So in other words, these 2 will remain as intact, only these 2 will be reduced. So if you look at these 2 things, and let me put the number here. So these are all the numbering given from here. So since it is a symmetrical molecule, you can start from either left hand side or right hand side. It is going to be one and the same. So this is the first bond, and that is remaining intact, that doesn't change. But here if you look at these two hydrogens are in the cis orientation. Similarly, these 2 hydrogens are in the cis orientation. So in other words, the Lindlar catalyst reduction reduces these 2 alkyne bonds into cis orientation only. So that is the only thing we have to remember, and that is how we wrote this product. Now on heating, what actually happens is this compound undergoes conrotatory 8 pi electrocyclization reaction. So this is a very crucial one, and this is a symmetry allowed reaction, and here the pi bonds are actually properly positioned for the perfect overlap. So when the conrotatory 8 pi electrocyclization occurs, we can see the shift of electrons, because 2, 4, 6, 8 pi electrons are involved in this reaction, and this is a conrotatory closure. So this leads to the 1, 2, 3 double bonds are there. So, and this is a 8-membered ring. So cyclooctatriene is formed in this reaction, and this is a very facile transformation, because this reaction involves a transition state which is having Mobius aromatic nature. So that is the reason this cyclization is a very facile reaction, and once the cyclization happens, we still have 6 pi electrons involved in this reaction. So these 6 pi electron can also undergo further cyclization. So at this time they undergo disrotatory 6 pi electrocyclization. So this gives, we are starting with a monocyclic ring that leads to the bicyclic derivative. So we have the cyclized product as shown here. We have a 6-membered ring, and we also have a 4-membered ring, and the bond, the first bond is formed between the atoms 2 and 9. So that is what is shown here. In the final product, we can say the 2 and 9 are having this blue color bond, so that way you know what is the bond that is formed. And in the second electrocyclization, that is the disrotatory 6 pi electrocyclization, there is a bond that is formed between the atom 3 and the atom 8. So that is where here we have the other bond that is formed, and in this particular case we have the cis orientation of the final product that is formed in the ring junction. And these two groups that are present in 2 and 4 are 2 and 9 are trans to each other. So this is a very specific cyclization, and based on that we can say this is a very specific case of a bicyclic ring formation, because if you look at the functional group, actually though alcohol is present in that one, the alcohol is not involved in any of the reactions. It is only the alkenes and the alkynes that are involved in the reaction. So the alkyne is converted to alkene, and when all the alkenes are there, they undergo the 8 pi and 6 pi cyclization to give the bicyclic system. So these kind of very difficult reactions are mainly used for the synthesis of various natural products, especially the ND-andric acids D, E, F and G, like various ND-andric acid derivatives are formed. This was actually Casey Nicolau who had actually done an elaborate work on these kind of cyclization reactions. So this is a very crucial reaction, and this is a very highly facile reaction because of the Mobius aromatic nature that happens in the 8 pi cyclization system.